Hi there, in my last video you saw me measuring RPM using a modified frequency counter. I thought it might be interesting to have a closer look at the setup. You notice there is a breadboard circuit in the foreground and a sensor on the helping hand. As a sensor I picked the TCRT 5000 reflective sensor because it's inexpensively available on eBay. It uses infrared and also it claims to have a daylight filter. I found that it sometimes had trouble picking up a reflection if the sensor was directly facing a window in the background. It did not seem to be bothered by light from other directions, particularly my room lights, which are all LED based. The recommended circuit for Arduino projects is shown here at the bottom, and that's what I used. However, I did not have any luck when connecting the signal directly to the input pin of my counter. This was strange because that pin is a proper Schmitt trigger input. Then I remembered that I had modified the frequency counter PCB to have a 1 transistor preamp instead of the silly crystal tester, and because the output of that preamp is DC coupled to the PIC16's input pin, anything else connected to this pin needs to pull the combination of R3 and R4 down to ground to be detected by PIC16. By the way, the preamp input itself is not suitable for RPM measurement because it's AC coupled and not suitable for such low frequencies. As you can see, with the recommended circuit, the TCRT 5000 pulls the signal high when light falls on the phototransistor. I could have reversed the circuit and put the resistor in the collector lead, but that meant desoldering the resistor. As this was just for a quick test, I left the sensor as it was and connected the signal to this super simple breadboard circuit on the right that provides ample pull-down power to make the whole thing work. A close-up of the sensor mounted on a little PCB. The LED is the blue part while the phototransistor is all black. I left the legs rather long in case I want to reuse the sensor somewhere else. Because the counter is such an inexpensive and versatile kit, I bought a second one from China via eBay. On that one here on the left, I did not populate the crystal tester or my preamp modification. This counter can of course directly connect to the sensor without the breadboard, but before we go there, it may be interesting to note that these two kits, bought about 1 year apart, are very similar but not identical. The key differences are the 7 driver resistors, 1K on the new board versus 220 ohms on the old. The 7 segment displays are a different brand, and they are just 3 pins, minus, plus and in on the new counter versus 4 pins, minus, plus, in and G for ground on the old. The G is connected to minus anyway, so that's not really necessary. On the left is the new kit. Notice that the character height is slightly smaller, but the real difference is the effectiveness of the LCDs. For the same current, the new display is almost 20 times brighter. This is while the driver resistors have increased from 220 ohm to 1 kilo ohm in the new kit. With that change, the LED current is down to 3 milliamps compared to 14 milliamps in the old kit. The slightly different display size isn't very noticeable unless you hold them very close and compare them directly. It is hard to compare brightness. I have removed the red filter to see the LEDs directly. Reducing the camera exposure helps a bit. I would say that the new count on the left is still somewhat brighter than the old one. With a reduced exposure, you will notice on the new display that the last digit is slightly less bright. Without going into details, that is caused by the trick that has been used to multiplex a 5th digit when the PIC16 has only enough outputs to directly drive 4. This circuit is of course the same in both kits, but the 7-segment display in the new kit seems to show the difference more. But anyway, the effect is tiny and you would normally not notice it at all. The old counter uses 20.75 milliamps, while the new counter uses only 16.54 milliamps. If you wonder why it isn't even lower, keep in mind that the new counter is still somewhat brighter than the old one and the display is multiplexed, so this is the average, not the peak current. Anyway, back to RPM measurements. This is the same setup as shown in my previous video, but with a new counter that doesn't need the additional breadboard circuit. If you build a counter with a crystal tester circuit populated, you should still be able to use the sensor circuit directly because the tester is AC coupled to the PIC16's frequency input pin. Let's test some more stuff. I made this disc out of scrap cardboard, gluing a half circle of aluminum foil on the front and back. The back part is just for balancing and not necessarily pretty. I had a spare spindle from a sanding disc, but a long machine screw with a nut would do just as well to hold the disc. Using the disc to measure RPM of this drill works just fine and allows quite a distance between sensor and disc. Having the disc in the chuck of the drill is one thing, but I was wondering if there was an easy way to measure RPM of the drill while using it for drilling. Since the drill chuck is black, I used sticky tape to temporarily fix a scrap of aluminum foil on the part of the lower chuck. Of course, in reality you would do this more carefully. It is just for testing. This method works just fine. If this drill would be in a drill press, it would be easy to attach the sensor and measure RPM that way while it's in use. Let's try more speed. The Dremel should be good for more than 10,000 RPM. It's a bit tricky to get the right position to the sensor, and I was worried the flimsy disc would disintegrate. But we are getting close to the maximum range of the counter. So what about a real propeller? It is white and so gives good reflection against the background. And sure enough, we get a reading, but it's not the RPM. See that? Each time a prop plate passes the sensor, we are getting a single pulse, which the counter momentarily reads as 1 Hz or 60 RPM. Because there are 2 blades and each gives a reflection when passing the sensor, we are getting 2 pulses per revolution, not 1 as with the disc before. The more blades, the more pulses per revolution. So rather than doing the maths, I decided to change the counter's firmware to allow measuring props or fans with up to 4 blades directly. When the counter starts up, it now displays for half a second what mode it is in. Frequency in this instance. To change it, hold the button while powering the counter up and it will cycle through the options. Frequency RP equals 1, RP equals 2 to RP equals 4. Release the button while the desired mode is shown. In this case, RP equals 1. It stores the mode in EEPROM, so when you power the counter off and then back on, it now shows RP equals 1 as the default. It shows RP and not RPM because there isn't a good way to show the letter M on a 7-segment display. Besides the additional RPM modes, there are a few other improvements in the firmware. The key difference is that it's now significantly faster. The slowdown with higher frequencies was the main reason that I limited the frequency range to 100 Hz in the previous version. Now the range is 200 Hz, and that's because the least significant digit isn't accurate anymore if you go any higher. The other change is that the RPM continues to work even if the counter switches internally to frequency measurement instead of period. Of course, these extended ranges have less resolution, but that's still better than having no RPM readout at all. I'm not going into any further details of the changes to the code. If you are interested, all firmware versions can be downloaded free from my GitHub page as source code or hex file ready for programming into the PIC16. With the modified firmware, we can now switch the counter into RP equals 2 mode, suitable for a 2-bladed propeller. And now we are reading RPM and see about half of the readout from before, which makes sense. In case you're wondering why we are not getting higher values like those we saw when using the disc to measure RPM, turning a propeller and accelerating all that air means real hard work for the motor, and so the motor speed drops. Looking for more objects to measure, I found this USB-powered fan gadget that shows time. There's no problem measuring its speed with a 2-blade setting. Looking for more blades, I found a large 4-bladed fan to test. I removed the front protection cage for better access. The dark blue metal blades give only a marginal response, so the sensor has to go quite close. I stick with medium speed because at top speed the fan wobbles so much that the sensor is in acute danger of being chopped off by a blade. So to recap, with the latest firmware you can directly measure 1, 2, 3 and 4 bladed fans, provided you use the blades for reflection. Don't forget, if you do something like this and position the sensor accordingly, you must switch to 1-blade mode because only the blade with the foil creates a pulse. Setting the counter for 4 blades will read way too low RPM values. What to do if you have more than 4 blades? This computer fan has 7. The way to measure it is to use RP1 mode to get a reading and then use a calculator to divide the result by the number of blades. Because the blades are black, I used a piece of aluminum foil on the table on which the fan lies. That way the sensor gets a strong reflection from the foil, which is interrupted every time a blade passes. So in this case we read just below 16,000, slowly increasing as the bearing runs in because the fan is old and had not been used in a while. We need to divide the 16,000 or so by 7 to get the actual speed, which is about 2300 RPM. Well, that's it. I've run out of things to measure. Please leave comments, and if you liked the video, give it a thumbs up. Thanks for watching.